let's start this morning session with my co-organizer, Arthur Jaffe, who will review constructive quantum field theory.
So, it's a pleasure to be in the Simon Center, I should say, because the first time I was in Stony Brook, Jim Simons was chairman of the math department. So it's a little daunting task to talk about constructive field theory because there's such a big body of information, and I've made some choices, so I hope I'll be able to relate to people here. The background is that in physics we often isolate and describe. So there are all these famous parts of physics. We could go back to the ancient Chinese, but if we start in the 17th century with Newton, he wanted to study gravity, invented calculus, Maxwell in the 18th century, Gibbs and Boltzmann statistical physics in the 19th century, and then the pillars of 20th century physics, and they're all really understood at a very fundamental where they're part of mathematics. And in 1900, Hilbert formulated in the ICM in Paris as his sixth problem the question, can one axiomatize all of physics? Well, of course, that's a pretty open-ended thing. My teacher, Arthur Whiteman, said a great physical theory is not mature until it's been put in a precise mathematical form. And Einstein also was a fan of mathematics. He said the creative principle resides in mathematics. And perhaps it's true that pure thought can grasp reality as the ancients dreamed. But can we do that for quantum field theory? And we know that field theory describes physics pretty well. In fact, the most accurate calculations and experiments that have ever been done, the anomalous magnetic moment of the electron, now measured to 12 decimal places in the 2006 experiment at Harvard, which the end of 60-year progress was talked about as the physics achievement of the year by the American Institute of Physics. And it agrees completely with the Feynman rules. But 50 years ago, there were only exactly soluble models of interacting quantum fields, and others seemed beyond reach. And at that time, Arthur Whiteman and others proposed constructive field theory as a way to address that. So more recently, we know that physics has been the lighthouse for mathematics, with many ideas from physics pointing to connections between different parts of mathematics and to solutions of frontier questions in number theory, algebraic geometry, representation theory. But that's not the topic of this lecture, although there are many experts here in the audience. So the question is, can one make sense of quantum fields? And the problems, of course, come from the singularities. The fields are quantized supposed to satisfy at equal time commutation relations that have delta functions in them, and therefore if fields in the quantum world satisfy nonlinear equations, and we often think of the equations as the same equations as for classical fields, then the nonlinear terms will certainly be singular, and this is understood in physics terms as necessity for renormalization. And in addition, the standard Hilbert space, which one learns about for free particles, the Fock space, is not appropriate for interacting fields for Hogg's theorem and the infinite volume, as well as for other reasons. So that's the task, and there are three basic goals. One is to construct examples of interacting fields, determine some of their properties, and as a byproduct, try to develop new mathematical methods to understand these questions. And they're exact, algebraic, geometric, analytic methods, but really the focus of what I'll talk about is infinite dimensional analysis, and that's the part of quantum field theory that I want to emphasize. So I hope that this relates to other questions that people have talked about here, or will talk about, or think about. What is the short answer after 50 years? There's a mathematical framework. The results are non-perturbative, but motivated and based on perturbation theory. And that fits in nicely with the framework of physics, but there are some things that can be said, people say exactly, but they really mean non-perturbatively. And there are examples in 2 and 3 dimensions, 2 and 3-dimensional space-time of interacting quantum fields. There are partial answers in 4 dimensions. And there's some non-existence results in 5 dimensions or more. Some new mathematics has emerged with these examples, but it would be good to have much more, because to solve the unsolved problems, more is needed. So I'd like to start now backtracking and talk about the first property that we'd like to verify, namely the axioms. And we heard beautiful talk yesterday by Detlef Buchholz about the Hag-Kessler axioms, but I'd like to mention the 5 standard axiom schemes. There's the Whiteman axioms for expectations of products of fields. The Hag-Kessler axioms, which are algebraic, that we heard about yesterday. There's axioms of Semantic and Nelson for probabilistic fields, Markov fields. Osterwalder-Schroeder is an alternative for Euclidean Green's functions or fields. And then there are Hag-Ruel additions to the Whiteman axioms. And so let me say just a little bit about these before we get into further details. The Whiteman axioms start from the assumption that you want to have a separable Hilbert space, and quantum mechanics is usual on the Hilbert space, except the fields live as operator value distributions on this Hilbert space. So they have some fundamental properties which are very natural. It doesn't say much about their structure. They're covariant under Poincare transformations. There's a vacuum vector as a state, and the theory is complete in the sense that products of fields applied to the ground state is supposed to be a dense set in the Hilbert space. So the ground state, I should mention, is got because you can take the Poincare group to have a unitary representation on the Hilbert space, unlike originally in the algebraic approach where you take an automorphism group. But here you have a group of unitaries, and if you take the time translations, then by definition the generator is a Hamiltonian, and one of the Whiteman axioms said Hamiltonian has positive energy. There's also a clustering assumption which has as a consequence uniqueness of the ground state, and that may or may not be true in examples. Now, it's very useful to add a little to the Whiteman axioms to make them a bit stronger, and there's a fundamental bound that says the field operator, and I'm writing this for the Hermitian case where the field phi is Hermitian and the test function f is real, should be a small perturbation of the energy. So plus or minus the field can be added to the energy, and you get something that's bounded from below. And in fact, a sharper form of that says that there's some measure, the norm of f, of this test function f that averages the field, that enters the inequality in a linear way. And one consequence of this fundamental bound is that if it's true, then immediately you know that the field defines a unique self-adjoint transformation, which is generally denoted by the same letter, phi of f, the average field. And that being self-adjoint, it can be exponentiated to a unitary. It's just some Schwartz space norm or whatever. It's some Sobolev norm, whatever seems natural in the problem. The norm will depend upon the field, what Lagrangian or what example you're talking about.
Regardless of the choice of norm, you get the
You would like to have something like this for some norm. So for the free field, it's a Sobolev norm, h minus 1. So that allows you to define this unitary, which is the exponential of the field, and that gives the connection between the field theory and the local algebras, because if the test function f is localized in a bounded region, then this A is an element of Detlef's local algebra. Yes? H is the Hamiltonian. So the Hamiltonian was defined as the infinitesimal generator of the time translation. And Whiteman axiom says it's positive. So H plus 1 is greater than 1. And we'd like to jack up the Whiteman. Yeah, it's positive in the sense of its spectrum being positive. Right. And A less than B means that B minus A has positive expectations. Yes?
Can we hope for such a result if falling has a large dimension?
For free fields, it's okay. But in the existing examples, this is always true. In some singular cases, it may not be true, and it has to be modified. It's not actually necessary that phi be an operator, but it could just be a bilinear form satisfying this inequality. Like a delta function potential can satisfy this inequality with respect to the Laplacian on the right-hand side.
If phi has an anomalous dimension, that phi has dimension greater than 1.
Well, I'm saying in the existing examples, this is true. It may not always be true, but it's a reasonable thing, and it allows to connect up Whiteman and Hug-Kessler, if it is true. Where does that bound come from? Well, this is much more technical, so let's come back to that later. So sometimes it's also convenient to assume growth of the vacuum expectation values in the number of fields, such as some growth with some power of n factorial. Okay, so then the Hug-Kessler axioms we are very familiar with from yesterday. There's no need to say about anything more about that, except there's this relation to the Whiteman axioms. The Semantic Nelson axioms, classical probability theory gave great insights into framework, the connection with functional integrals, and this was talked about in a very lucid way by Kurt Semantic and formulated mathematically by Nelson. But it's difficult to check the global Markov property of Nelson. In fact, as far as I know, for interacting examples, it hasn't been done. But luckily, there's an alternative, which is the Osterwalder-Schroeder axioms, which are a little more general, apply to fermionic and gauge fields. And so I'm going to pass to them. Now, the Osterwalder-Schroeder axioms, which were motivated by these Semantic Nelson axioms, are axioms for a set of classical fields. And these fields generate some classical algebra. We can think of A of phi, an element which might be a product of fields averaged with test functions or sums of products, polynomial algebra. And the particular thing is that these fields, classical fields, are Euclidean covariant. So it's the analytic continuation of Lorentz covariance. And that includes reflections. And here I take the time reflection, which to be part of this Euclidean group. That's important. And there's an assumption that there's a Euclidean invariant state, which is invariant under any group element G, including the time inversion, and some clustering, which is equivalent to clustering in the Whiteman framework. Now, there's one more assumption for the Osterwalder-Schroeder theory, which is a little unusual, and that was discovered when they were postdocs with me at Harvard in the 1970s, and that is reflection positivity. And this sort of is the key connecting the Osterwalder-Schroeder theory, Euclidean classical theory, to the quantum theory. And it says that the reflection, and in this case the time reflection, is a positive, gives a positive expectation on A's functions and fields localized at positive time. And this is very unusual because you'd expect normally for positive functional not to have this time reflection, that A star A is positive if for any classical function A, and then a state would have a positive value on that field. But putting the time reflection in there is a little funny, but that's key.
So is star theta, is that a linear or
It's a classical field. Star is complex conjugation, and theta is unitary. Yeah, so the fact is that for every example of quantum mechanics that's been worked out, there's a way to use this positive form to define an inner product which turns out to be quantum mechanics. So it's explicit to do it for harmonic oscillators or quantum mechanics or free fields, and it should be taught in every quantum mechanics course. But perhaps it's not well enough known. And this is a method of quantization that from this positivity of the time reflection on positive time functions, you have a new inner product, and that turns out in the examples to be ordinary quantum mechanics, and that's the reason why it's so central. So it gives you a connection between the classical fields on the left and functionals on them, such as functional integrals or probability distributions, and some quantum mechanical objects on the right. And more generally, the expectation of a product of these classical fields is equal to the analytically continued to imaginary time, ordered, anti-time ordering with increasing time to the right, analytic continuation of vacuum expectation values of fields. And this phi should be a lowercase phi. These lowercase phi's are the quantum mechanical fields, and the capital phi's are the classical fields. So that's a misprint there. Oh, and the A is anti-time ordered. So that gives you the connection. And in fact, the Osterwalder-Schroeder axioms combined with some growth condition in the number of fields is equivalent to the Whiteman axioms with a growth condition. Yes?
Are these also equivalent to Semantic Nelson?
No. The Semantic Nelson is stronger, yeah. It's this global Markov property on the reflection plane, and this is not known except for as far as I know, for the free field. I mean, you have a Markov property on compact regions that's been proved by Albaverio and his collaborators, Hugh Krohn, but the global Markov property. I'd rather not get into this technical detail because let's talk about it at lunch. So what are the Hague-Ruel axioms? Here the Whiteman axioms are augmented in another way, where you assume that there's a isolated one-particle hyperboloid in the energy momentum spectrum. Now, that's a lot more than clustering or even exponential clustering, which would determine a mass gap. But that says that there's an upper gap in the spectrum. And the reason is that Haag and Ruel used this assumption in order to construct out of the one-particle states many particle in and out states. So you can construct the S matrix. It's a form of scattering theory alternative to Lehmann-Semantic-Zimmermann, which is very beautiful and just a consequence of the axiomatic framework in case that there's an isolated one-particle spectrum. So what is the basic yoga in constructive quantum field theory? You have to approximate the fields, get rid of the singularities in order to understand them, preserve what you can. And you'd like to preserve many symmetries, possibly, if you have special symmetries in the theory, either unitary symmetries or supersymmetries. You'd like to preserve reflection positivity, if you can, if you're doing the cutoff in the classical field framework. And generally, it's not possible to preserve all the symmetries you want and the reflection positivity, and you have to work quite hard then, if you get to the end of your construction, to check those things in order to determine whether the axioms are true or not, or more detailed things are true. But with these axioms, the way I stated it, it goes as far as determining one-particle states. Now, you want to get stability and maybe properties of the spectrum, expand to get control over individual terms. Now, there is a plethora of expansions in constructive quantum field theory, and I'm not going to get into the details of these expansions, but I will talk about some of the ideas that are going into the expansions. And then you use these expansions to establish localization when you can. And that is, you'd like to show that clusters decay if you have A and B, like Detlef had yesterday, two observables and two clusters, but now we allow these observables to be unbounded field operators, average, so they lie in separated regions, where R is the separation of the clusters. You'd like to have some norm on these products of fields, which is expressed in terms of the test functions, so that you have exponential decay. And that exponential decay is given by some rate, m, times the distance, or the mr is some scale distance, which, if you have some scaling, gives appropriate decay. And this localization or exponential decay is sort of crucial, and m gives a bound on the mass gap. Yes?
And there are theories that don't have mass gaps.
Of course. And so the constructive field theory works best with theories with mass gaps, and then when you don't have mass gaps, you have to stand on your head to make things work.
So when you don't have mass gaps, you try to do something with that with power law and something like that.
Well, you tried, for instance, if you have a phase transition and you have a critical point with no mass gap, you try to approach that from theories with a mass gap, or you try to approach these singularities in some reasonable way. And then you would get power law decay or something. Yeah. Okay, and then in the end, you want to remove the cutoffs and preserve all the structures. So to establish detailed properties of the limiting theory, for instance, if you destroy reflection positivity in your initial approximation cutoff, it may be very difficult to show that the resulting end limit has that property, because positivity is very difficult to establish unless you have a positive approximating sequence. So there's certain things that you like to preserve in taking limits. Others, like translation invariance, you might be able to show different limits or rotational invariance in different ways, give the same result, and lead to that invariance for the limit, even though that has been destroyed in the approximation. But each different example will have natural ways to do approximations. Okay, so let me first specialize to scalar bosons, because those were the first results. And so I talk about the two-dimensional nonlinear wave equation, which some people in the audience know very well. And in dimension 2, x vector is just one-dimensional. So, and for positive polynomial v and any positive coupling constant lambda, there's a existence theorem. And in fact, all these axioms can be established for small values of lambda. And for certain large values of lambda, by reparameterization, it's small values of another potential v. And this leads to examples. So these are the initial two-dimensional so-called P5 models, because v is a polynomial. Now, for small lambda, the vacuum is unique, at least in a wide variety of ways of removing the cutoffs. While for, say, 5/4, or for many other polynomials for large lambda, there's a phase structure where you have non-unique vacuum states. And so these things are established by so-called cluster expansions. So there's some expansions where you take the vacuum expectation values or the analytically continued classical functions corresponding to this interaction, and you have some approximation and then an expansion, and you use these expansions to pass to the infinite volume limits. And so the initial cluster expansion with Jim Glimm and Tom Spencer led to both some uniqueness for small lambda and non-uniqueness for large lambda of 5/4, where v is a quartic polynomial. So in 3 dimensions, the theory is super renormalizable only for 5/4, and there for small lambda, well, there's existence for all lambda, but for small lambda, the Whiteman axioms, the Hogg-Kessler axioms, and the Osterwalder-Schroeder axioms are known. And maybe, as far as I know, there's no similar result for large lambda. John might correct me, but no. But in the unlike the two-dimensional case, nothing is known, as far as I know, about the upper mass gap. Well, in the two-dimensional case, all axioms are known to hold. That includes the Hogg-Ruel axioms with the isolated one-particle states. And in fact, Spencer and Zerilli have proved in certain examples they're bound states. And in 5/4, there are no bound states. It's repulsive. But there are a lot of detailed results. And here's a picture of Jim and me some years ago. I wanted to throw in that one picture. And but for scalar bosons, there's also, as I mentioned, non-existence in 5 or more dimensions. And here there's it's for 5/4, and that's the only one that, as far as I know, is known. If you take a lattice approximation, so you cut off using ultraviolet cutoff using a lattice, and you have to assume unbroken symmetry phi to minus phi in the ground state, and then the connected 4-point function goes to 0 in 5 or 4 more dimensions. This is a result independently of Froelich and Michael Eisenman, and depends upon some correlation inequalities, which are generalizations of Leibowitz inequality, and established, well, through Zemansk's picture by Bridges, Froelich, and Sokal. So these are very interesting inequalities, but it's a negative result that in 5 or more dimensions there's no interaction. The field is so singular for 5/4 that if you try to define a solution to the nonlinear equation, you're forced to take lambda equals 0. Now, in 4 dimensions, Froelich has pushed that to the edge. 4 dimensions is the borderline dimension where the coupling constant is dimensionless. And it's almost proved that it's trivial, but it's not completely nailed down. There's some technical assumptions along the way. So there's still room for improvement there. And we really don't know. Normalization group picture suggests that it's trivial, but I'm not sure. I was talking this past summer to Ed Nelson, and he was suggesting that maybe it is not trivial. And I don't take things that Ed Nelson says lightly, so he wasn't really sure, but it's really a question up in the air. This choice of lattice regularization has to be something like something where you have the standard correlation inequalities, because these bounds depend upon correlation inequalities. Yes?
The idea here that you always that you expand around the Gaussian fixed point. I mean, would it be possible that there's a version of the non-Gaussian fixed point of those?
I don't know what is going on in Ed Nelson's head, but he made that comment to me, and he said he's very fascinated by it. Tom?
Well, there's a comment that I guess that probably goes back to semantics that says these scalar bosons can be written as interactions of Brownian paths.
Oh, yes, right. So yeah, thank you. So Kurt Semantic suggested that since Brownian, so the interaction in 5/4 theory can be considered as the intersection of 2 Brownian paths. And a Brownian path wiggles so much that it has Hausdorff dimension 2. So in space-time of dimension greater than 4, you don't expect generically 2 paths to intersect, while in space-time dimension less than 4, they generically do intersect. So that fits this picture of interaction in dimension less than 4 and no interaction in dimension greater than 4. 4 is borderline, and you have to be very careful about what properties the random paths have. And it's one of these renormalization properties that's just a hair's breadth away from making this into a theorem. Yeah.
Briefly recall something I mentioned in the discussion yesterday, that we now, for I guess more than 10 years, think that, are pretty confident that there are interacting quantum field theories in 6 dimensions. And they certainly don't contradict this theorem because they have fermions and
Right.
serious degrees of freedom, but they contradict all this other intuition about how this should be possible. Greater than 4 dimensions, and it's just this axiom and mystery how this could be possible at all.
Okay, so here's a small subset of the scalar boson, a few references. In fact, these are not references to papers. These are references to series of papers. So you can see that I had a difficult time in trying to prepare this talk. You could give a talk on a subset of any of these things. And I have to say that there are so many people in the audience who are referred to here that I beg your pardon if I haven't included work that you think is very important. But there must be, I don't know, 1,000 papers. And so I'm just trying to say a few things that I think people should know about. And other people would have different opinion about what should be talked about. So let's come now back to the simplest example, the standard Gaussian, which is the free field, the countably additive measure. And the two-point function or covariance of the free field is the free Euclidean propagator. It's just the inverse of the Laplacian plus a constant, which gives the exponential decay rate and therefore the mass. And C is reflection positive if and only if the Gaussian with that covariance is reflection positive. That's a simple fact about matrices. And there are two methods to establish this. One is to do the calculation in Fourier space, which is, if you're on Euclidean space, the simplest thing. But there's a more abstract method, so I'd like to mention that because I don't think it's very well known. And that is that it's equivalent to monotonicity of some classical boundary conditions on the Laplacian. Namely, the Laplacian with Dirichlet boundary conditions, or the covariance with Dirichlet boundary conditions on the reflection plane, let's say t equals 0, is less than the Neumann boundary condition. Well, we know this in quantum mechanics if you have a box, that Dirichlet eigenvalues are greater than Neumann eigenvalues for the Laplacian. And the inverses go in the other order. And this Dirichlet-Neumann data on the reflection hyperplane for this example gives the reflection positivity. And that's a classical inequality in partial differential equations. So, for instance, we can imagine that in terms of the Laplacian on some thing with symmetry, where the Green's function C is the potential at y due to a test charge at x. And if you take the reflected point x through this, let's say the vertical line here is the time zero plane, where we've taken a reflection symmetric situation, then the Dirichlet Green's function is the difference between the Green's function and its reflection, and the Neumann Green function, the sum. So if these happen to be Green's functions with positive kernels, integral kernels, then they're pointwise positive, but that doesn't mean the spectrum is positive. But this Dirichlet Green's function actually has spectrum less than the Neumann Green's function. And so this method is useful for sometimes looking at situations which are not ones where you can calculate the Fourier transform. So therefore you could set up a reflection positive Gaussian in this situation, and that gives possibility for duality, because if you have two different time reflection planes, one might be a time plane and a space plane, then you get two different Hilbert spaces of quantum theory, two different fields, and two different ground states, and some relation, if these come from the same functional, between the two. So this gamma is just a map from one plane to the other. And so this gives some type of duality, like the dualities that many people here in string theory study. And I think this is something we're exploring. The consequence of having this reflection positivity is one tool to study what Hilbert spaces emerge. So I'd like to mention one other thing, that you could have a non-Hermitian covariance C. For instance, if you are on Rn, you could define it by the Fourier transform, the Green's function C, and that means that the Fourier transform is not a real function necessarily. In the ordinary case, the Green's function would just be the Fourier transform E squared plus K squared plus this M squared. Yes?
Can you get the Hamiltonian if you have a funny surface like that?
Yes. Oh, I don't know. I don't know. This is something that we're studying. So the time reflection positivity, or the one particle Hamiltonian coming from this one, is just the ordinary thing plus this boost k dot v. And this one happens to have two reflection planes. It also has a reflection plane along this vector v, which is given. And so if you take the reflection of the spatial part of x to x minus multiple of v, then you reflect into the around the vector v. You also have a reflection positivity, and you get a different. In this case, you get a different Hamiltonian, which is so this physical system, this is actually, so you have a complex covariance. This arises this was suggested by an old paper of Heifetz and Osipov, and it's something that Christian Jekyll and I are studying with a student. And so the Hamiltonian is just the Lorentz boosted Hamiltonian. It's the free Hamiltonian, but Lorentz boosted. And the problem with this situation is that you don't get a complex measure because this C can be decomposed into the real and imaginary parts. And the real part K is positive, but there's a criterion when you can get a complex Gaussian by inversion, and that says that the imaginary part L with respect to K has to be Hilbert-Schmidt, or it's square summable. And so it's square is trace class. But that's certainly not true here. It has continuous spectrum. So even with some type of cutoff, it wouldn't be the case. So there's no, in this case, there's no complex measure, but you still have a Gaussian's functional that can be used to study all sorts of things. And this is the subject of a couple of papers that we're writing now. And Christian and Robbie Martinez and myself. So there's if we come back to the usual standard Gaussian, then the interactions are obtained by perturbing the action. And you put in the factor e to the minus a, where a is the interaction action, and then try to normalize this. So you start with in the normal case, C is just minus and plus 1, or m squared inverse, and you try to find this measure, this formula introduced by Semantic and Nelson. But so there are three methods I wanted to talk about to study these problems. I don't know, should we just go through to the end? Okay. So the first method is to look at the low and high momentum parts of the action. So you put in some type of cutoff, and high momentum cutoff kappa, and define the deviation as just the difference between A and the cutoff A. And there might be some other cutoff in the background to establish the existence of the cutoff model, but now you look at that cutoff model and you ask, is the low momentum part bounded non-perturbatively? And that means that the low momentum part of the action, e to the minus a, has an upper bound given by that non-perturbative factor in the cutoff. And then the second part of it is to study the high momentum tail and to show that it is large on a very small set in the functional integral, in the Gaussian that's being perturbed. And this method will work if this divergent factor from the low momentum part is overwhelmed by the convergence factor from the small measure. So that's like showing that the integral of 1 over square root of x down to 0 exists. And the product is small, it will work. And that's the basis of the elementary methods that were used. Now, this sort of method has been extended. You use this method in a finite volume, and then you show that different volumes have some decoupling, some localization, one volume from the other. They decay between different volumes. And it might be that you have to take the initial volumes very small, which was the way it was implemented in 543 originally, and served as the basis for that phase cell expansion, which is sort of related to these cluster expansions that people talk about now. So the second thing is to organize this a little more systematically. And this to look on some momentum scale and to integrate a range of momentum in the functional integral in the Gaussian, and see if estimates on one scale lead to estimates on the next scale. And originally, this was implemented as an inductive scheme in the 543 work, and then extended by to a multi-scale cluster expansion by, well, this is sort of the basic idea in many of these cluster expansions, both the work with Jim and Tom and also Mannion Senor, many other people. But then these cluster expansion methods depend heavily on the mass gap. So you want to have some exponential or almost exponential rate of decay and decoupling. And that allows you to add interaction outside some large region and sum that distance out to infinity because you're summing these exponentials. But what was proved and probably isn't known is that you can actually span states in the Hilbert space in the two-dimensional models for small coupling constant up to an arbitrary energy by polynomials in the field applied to the vacuum. And if you want to go up to an energy which is close to the mass, so you have some given epsilon greater than 0, and you want to go up to n times 1 times the mass, then it's sufficient to use polynomials of degree n. So usually one focuses on the case n equals 0, and that's the ground state where you can go up to the next excitation level by separating out the contributions using a cluster expansion of the ground state. But in these particular cases, you can actually go arbitrarily far, but the problem is that you have to choose your coupling constant after picking n and epsilon, so that the radius of coupling that you can prove these estimates shrinks to 0 as n gets large. So it's certainly, this paper, I think, should be reworked and with an idea to trying to understand asymptotic completeness. Yes?
I was going to ask if one found a way around this difficulty, if the radius shrinking with n, would one have asymptotic completeness?
Well, not, well, it's, I mean, Tom and Zarelli proved asymptotic completeness in certain examples up to, what, 4m? But it doesn't immediately follow, but you'd be well on the road, and intuitively it should follow. But, yeah. I don't know, but it looks very promising that you could get there. Now, the third method I wanted to comment on is the renormalization group method, which has many of the same ideas, but it's much better organized because you try to, instead of inductively defining the expansion, iterate an expansion. That is, after integrating out a certain set of momenta on length scales, you would like to have an effective theory. And this method has received a tremendous amount of study. There's a huge set of papers. I mean, it was Gallavati and Niccolo and their Benefato and their collaborators, Gavensky, Kupianen, and Bridges, Dimmick, and Hurd have a method. Vincent and Malik have worked on this extensively. And there's a relation to the revised form of the cluster expansion that was ventured by David Bridges and H.T. Yao. And yet, still much more work has to be done. And so I come back to this later. So then there's this other thing I alluded to, the correlation inequality methods. These are correlation inequalities like in statistical mechanics, where certain correlations, the expectation of AB minus the expectation of A times the expectation of B, are positive. And other related inequalities, and they're very useful. This approach was used by Guerra, Rosen, Simon. Elliott Lieb made many contributions. Key to the negative results for 5/4, but also to many positive results for P of phi models in the bosonic case. And there's another method which I just should mention exists, that is to remove cutoffs using convergence, some compactness argument, convergent subsequences. And that really is dangerous. And the reason I want to mention it is that the problem with those methods is that you don't know that symmetry is continuity, or much of what is true for the approximate theories goes over to the limit. Those methods were used by Albavarian, Hercron, and by many people, including Jim and me, to construct certain limits. The initial infinite volume states were constructed that way. You get a great deal of information about local operators, but the information about the states is pretty weak, and so in general, if you can steer clear of compactness arguments, keep away from them. So what are some open questions? For the scalar cases, use new expansions to get the upper gap especially. I mean, all this work that many papers by these different groups are oriented toward doing vacuum cluster expansions. It would be very nice to redevelop, as I said before, the higher, at least the one particle cluster expansions to get the upper mass gap. This problem that Mike proposed of looking at trying to find a useful topology on the space of solutions, which was one of the reasons Mike suggested organizing this meeting in the first place. And that's something that in principle could be an output of the cluster expansions. And in dimension 3, you would like to establish isolated one particle states, that is the upper mass gap, or results about the mass gap for large coupling, because there should be a phase transition, and that's not established in that model, nor the stability of the integrals about the large coupling region. So those are very interesting questions. These new expansion methods presumably would be useful in other types of work. And I think that one thing that's important is that constructive quantum field theory has focused on two things. One is building machines to study problems, but also to solve particular problems. And maybe there's too much focus on solving particular problems, and a little more focus should be made on looking at methods which would be useful and fit centrally into mathematics. So I mentioned earlier the partial results about non-existence in 4 dimensions. We'd like to know one way or another if that really works for scalar bosons. And there was all this talk about whether the standard model could exist yesterday, but these correlation inequalities are only true for single component models. So with a continuous symmetry, you're out of the ballpark where at the present time you could prove things mathematically. Now, only now I get to fermions. So let me start with some basic comments. The quantum mechanical fermions satisfy these commutation relations that I mentioned at the beginning of the talk with a delta function, but the classical fermions we know from Berezin are Grassmann. So how can you connect these two? It's a little more complicated than in the scalar case. But still, in the free case, it's possible to find classical fermions, capital psi, that are anti-time ordered products of quantum fermions. And these are also discovered by Osterwalder-Schroeder, and they require doubling the number of degrees of freedom from the classical case. Yes?
Why is doubling that?
Because otherwise you would have a singularity coming here. You need to, you eliminate the singularity, you get the symmetry from putting in the anti-time ordering. But even for 1 degree of freedom, you can write down the constraints and you find that there's no way to implement with the same number of degrees of
So it
freedom.
has nothing to do with reality conditions.
No.
Because heuristically, Euclidean fermions are described without any doubling. People who do the centered model, for example.
I don't know. I'd like to learn this, but and we're going to have a talk about it, I guess, tomorrow by David Kaplan. But as far as I know, you can't implement the required and the required Grassmann structure, and also agree with the usual fields expectations without increasing the number of degrees of freedom. You don't actually have to double. It's somewhere in between a factor of 1 and 2. And so there's some arbitrariness when you double. And
I probably shouldn't say anything, but it doesn't sound right.
yeah, I agree. And so that's something that should be looked at. But the present framework uses these doubled fields. Well, you can build a Fock space over the Grassmann fields, and the no particle expectation in that Fock space, I call it omega E for classical, just agrees with the time-ordered expectation of the usual Fermi fields. And there's a similar construction for the Dirac case.
Are we? There has to be, because the Dirac case is just two copies of the Myron.
Right, exactly.
But are we just trying to find Euclidean correlation functions for frameworks that analytically continues to this stuff on the left?
As Grassmann, and they have to have the Grassmann condition.
Which means that?
It means they anti-commute. So at equal time, they don't have this delta function. What?
You need a Clifford algebra to pull the process. But the thing on the left hand side.
In which? The classical case?
Yes.
No, but you want to do it in the Euclidean case, so this is replaced as a generic case.
Yeah. This is Euclidean. This is real time. Equal time.
Well, yeah.
I,
At equal time, it doesn't matter for Euclidean or Lorentz symmetry. So if we have decided that we don't want to, maybe this is the wrong thing to do.
yeah, I don't want to just, I mean, this is tangent, but it's very important that, yeah. So here we have the anti-time ordering, so it's not, it wouldn't be true without putting in the anti-time ordering. The right-hand side wouldn't be skew symmetric. Okay, so the generalized Yukawa models have been constructed using these methods. And in fact, you generally integrate out the fermionic field, which is quadratic in the interaction, and get a determinant or Pfaffian, and study the bosonic integral with that factor. And the Whiteman and Hug-Kastler axioms for these generalized Yukawa models in 2 dimensions have been established by Cooper and Rosen and Menyon Senior using cluster expansion methods. Originally, finite volume things were done in the canonical approach in Hilbert space. And there's some partial results in d equals 3, but they don't get to an axiomatic field theory. So with supersymmetry, you can relate these two potentials and get a Wess-Zumino model. if V1 and V2 are given in terms of a superpotential W. And so in the charge case, this was done, and it gives rise in a finite volume to a trace class e to the minus h. So in the complex case, there are actually no renormalization counterterms. Well, in the real case mentioned before, renormalization, mass renormalization, and some other low-order renormalizations are necessary. And this happens to be related to index theory and to cyclic cohomology, but I think I'll skip over this because I'm a little behind. But there is this cyclic cocycle whose pairing with square roots of unity. A is a square root of unity, some operator in the local algebra, which is a square root of unity. And this tau is a cyclic cocycle, and there's some index type formula that is a sum of differential forms of all order that gives this pairing. And that's a simple formula for it. Now, let me come to gauge theories, because everybody here is interested in that. And so there's two methods that have been studied to regularize lattice and continuum, and they both have advantages and disadvantages. There's different schools of thought. Now, the Wilson lattice action, where you assign bonds of the lattice to elements of the gauge group, is nice because it preserves Osterwalder-Schroeder positivity, or reflection positivity. And this was established by Scalar and Osterwalder just by taking a gauge that is identical across the reflection plane. And Vincent likes to use continuum regularization, and so there's a whole school of papers and extensive things written with continuum regularization where you run into different difficulties. So the problem with the gauge theories is, in the supernormalizable case, not too difficult, but even there's if you couple an abelian gauge field to an electromagnetic, a U1 field coupled to 5/4, then you get the Higgs effect, but this work with Balaban and John Embry and with David Bridges for the uniform mass gap on the lattice, still there's no complete construction, as far as I know, where you take the limit of zero lattice spacing. So is that correct, John? So I think that it's possible to, here there was an expansion where you use different gauges on different length scales, and you have to use a sequence of gauges from an ultraviolet gauge on the short distance scale to infrared gauge when you get up to macroscopic scales and you have the mass, but still controlling not just the uniform gap on the mass for different lattice spacings, but the limit as the lattice spacing goes to zero hasn't been tackled. So it would be good to go back and study that in the simplest case here, which is the two-dimensional problem.
Why do you need gauge fixing on lattice?
Well, you want to understand the infrared singularity in a Lorentz gauge, where you understand how the Green's functions work at short distance, and then when you get to macroscopic scales and you want to show the existence of the exponential decay, it's useful to go into a different gauge. And if you have an iterative scheme, you actually you use different gauges on each intermediate scale, going from one to the other.
What's the virtue of Wilson's formulation was that we do not have to gauge fix.
Well, but one of the problems of constructive quantum field theory, and this is something that may be a philosophical point, it's good to emphasize, that is sometimes you have what looks like a certain apparent thing from the point of view of physics. So, for instance, in supersymmetry, you have cancellation of infinities for complex fields, Wess-Amino interaction. And so you think the theory is finite, and yet you have to pretend it's not in order to do the intermediate estimates. And then you find out in the end it's okay. And even though you think there's a physical principle at work in the end, it might not be possible in the intermediate steps. When I was saying you want to preserve as much as you can to preserve all you want. And so to analyze the problem in detail, you may need to look at things where you don't see the forest for the trees for the moment, and then you get up to a scale where you see the trees. So in Yang-Mills theory, Thaddeus Balaban wrote many papers about the lattice problem. And there's a beautiful review from last October by John Dimmock, which I found on. John just got here last night, and unfortunately, I wanted to have John make some remarks about this, but he was not able to prepare for that. So, but if you look on John's internet site, you can find this. And so the action has U as product around a Wilson plaquette and of the gauge group variables. And so this is the action, and the continuum method has the problem that then you don't work with the Wilson loops but as observables, but the gauge fields themselves, the F mu nu. And there's this majestic paper in 1993 by Mannion, Senior, Riverseau, where they claim to understand the finite infrared cutoff, that is finite volume Yang-Mills theory in the continuum limit. But I just have to admit that I've never been able to go from beginning to end of this calculation, and I don't know. I think it would be very good to redo that work too in a form that any mathematician could follow from beginning to end. So Balaban's work on the lattice gauge theory has looked at the effective action and again gets uniform estimates and in principle gives insight on how to construct the limit as the lattice spacing goes to 0. But it doesn't deal with the Wilson loops, and the continuum limit is not taken. So there's the work even in the finite volume or infrared cutoff theory, it would be a tour de force in my mind to give a complete mathematically understandable construction of any non-abelian Yang-Mills theory with a semi-simple gauge group. So I called dimension 4 the Wild West because there are a lot of people in this arena and many things going on, but we need to complete the bounds so that they're understandable to more than the authors of the paper. And we need to, in the case of the lattice approach, include Wilson loops so that they're observables. Yeah.
When we speak of Wilson loops, there are two things we could consider. One is that something that's supposed to have finite size or we have a continuum limit. So it converges to what is called a Wilson limit.
Right.
Or we could take a little maquette and try to get something that converges to a local gauge invariant.
Yeah. Well,
Which are you thinking?
well, I was thinking of observables of finite size, but either one would be a major step. And if you have the local fields in the limit, then you could look directly at the Whiteman type axioms. But it would be technical breakthrough to redo the estimates, including the observables. So far, this has. What? Pardon me? Yeah, they haven't been done. So I think, I mean, I always encourage Static to work on this problem, and he told me that, well, he was a little depressed because he thought I was the only person interested in the outcome. And I tried to convince him that this wasn't the case. And then a real disaster happened. Maybe I should tell this story. Static, he was living in Cambridge, and he liked to go away during the summer and visit his friends in Brazil and other places. And he also was very frugal, so he would save money by packing up his belongings and moving out of his apartment and finding a new apartment for the fall. And in one of these moves, the moving company lost his thousands of pages of notes on Yang-Mills theory, and he said after that he could never go back to the problem again. Yeah. So now we need to, even in finite volume, to establish a uniform mass gap in the continuum limit would be major breakthrough. But to establish the infinite volume limit, that's another story. So I'd think the finite volume Yang-Mills, at least in principle, appears within reach. But all constructive field theory methods to pass to the infinite volume limit that I've talked about here depend upon using the mass gap to add interaction at a large distance and use the exponential or some sort of decay out to the large distance to sum over distance to add interaction out to infinity. And so if you were to follow that route, you would have to solve the mass gap problem. And that's something that in the Yang-Mills theory, the mass generation isn't completely understood from the point of view of physics, so it's a very different kettle of fish. And so how much do you have to include to have a well-behaved theory? We'll believe that non-abelian gauge theories, the semi-simple gauge groups work. We believe that some others work. I don't think we need a theory of everything, but we don't know. And the modest proposal would be to try to renew attempts to isolate and explain, focus perhaps on first Yang-Mills, and develop a machine which is a little more mathematical and intuitive, where you can put estimates in to use it for this problem, but also oriented towards some more general applicability. Some black box like partial differential operator, some pseudo-differential operators in the theory of partial differential equations, which would give you a black box output, which would be useful. And then you also have to study your singularities, so do things like Jaffe and the other people in nonlinear wave equations do in isolating the difficulties. But to use the methods, I think it would be good to solve the earlier mentioned problems in 2 and 3 dimensions, to construct SU2 as, I think, I mean, some people like large N, but I think just doing SU2 at the other end of the spectrum would be also very intuitively beautiful. And in fact, we believe that QCD should work, but for the infinite volume limit, that really poses a difficult problem. But I think just a finite volume solution would be a major, major achievement. And the problem is that each of these questions at the end of the list require an order of magnitude more analytic difficulty than anything that's been done up to now. And so it really has to be organized in a way that's comprehensible. And each appears to need some new mathematic structure. Even in the case of the bosonic field theories that I mentioned, the 3-dimensional 5/4 theory gives rise to a new class of probability measures, those reflection positive Euclidean invariant countably additive probability distributions on R3. And I mean, I heard this hasn't percolated into the mathematics community as far as I know. It's very funny that there are all these mathematical objects that, even from the point of view of standard probability theory, look a little bizarre. And a couple of years ago in Dublin, the famous probabilist Varadon was giving a public lecture about the applications of probability theory. And so I asked him at dinner, why didn't he mention quantum mechanics as an application of probability theory? And he said, oh, quantum mechanics, it's not that important. So I think that it's really good to work out these mathematical problems in a way that connects into the mathematics community, as has been done in all these geometric questions that touch on analysis that many people in the audience here are expert on. And don't lose sight of the fact that we might want to modify space-time and use some non-commutative space, as was mentioned yesterday by Detlef. But to be modest and solve these problems, one needs some young, genius mathematical physicists to work on them. I feel I've been doing this for 50 years, but we need some young people, many young people, so send some students our way. And I hope this will provide an answer. Thank you. Yes?
You began your talk by discussing the great success of QED to 10 decimal places, but none of this has got back to that. Can you get back to those questions of constructing QED?
Well, the thing is that, thank you, Barry. So we believe that QED satisfies, it falls in the category of things that don't exist because it's not asymptotically free, like 5/4 and 4 dimensions. So it's believed that the best thing that's known on this planet, this anomalous magnetic moment of the electron, which the most recent experiment was 2008, and that was done by Jerry Gabriels at Harvard. Following the experiment in 1947, which was the first deviation by Cush, found the 1.001, and I counted up actually that the work, theoretical and experimental, connected with this 12 decimal place number touched 23 Nobel Prize winners in physics. It's an unbelievable number. So we believe that that theory is inconsistent. So we believe that you cannot isolate and explain quantum electrodynamics, and physicists say you have to include other interactions. You have to include non-abelian gauge field.
So with this 12 decimal places, were weak interactions included or not in the calculation?
No, I believe that's just QED.
They're small. They do it.
What?
They did experimental. They did experimental input until up to 2.5. For the electron number or for the mu?
I thought for both.
Maybe barely.
It's just at the borderline, so I'm not sure.
With the order alpha times m electron over m W squared.
Right.
Which is about 10 to the minus 12.
Right. So, but yeah, and you also have to, you're assuming that you can measure the measure alpha. So you could turn it around and make this experiment a measurement of alpha, but use the Josephson junction methods to get an independent value for alpha. Yes, Spencer.
I would like to return to the SU2 four-dimensional Young-Mills. First of all, thanks for this focusing again on this fascinating problem. It would be good to return to these things that we did 20 years ago or so. Sometimes it's good perhaps also to mature the thing, put them a bit in the fridge. And I have the impression that the dispute is not so much over cutoffs, because there is this lattice cutoff, there are these momentum cutoffs that are now, I think, quite well understood, which kind of terms you need to be on the right trajectory for a momentum cutoff. For me, the essential difficulty is to progress on the multiscale expansion formalism, so that, as you said, it could be understood by more than the author. And because it's already difficult, this multiscale expansion, when you have just the normalization theory. And then to add the word identities of the kind of gauge invariance you want to control makes it almost impossible to master. So my impression is going to progress by slow, small technical improvements in the formalism. For instance, I think that one of the difficulties is that when you have multi-scale expansion, you would like to compute connected quantities at each scale in order to implement the renormalization group. Then at each scale, you should sort of do a cluster expansion, and then there's this problem of so-called hardcore constraints on Meyer expansion. And we found, maybe Malek, you will correct me if I am wrong, that this was a really hard point in the multi-scale expansion. So there has been several attempts to automatize this and make it more comprehensible. One was by Bridges, and he used this formalism, introduced a kind of a strange exponential that does directly this computation. Then recently...
The Bridges and Yao.
Yes. And then recently, I stumbled on another way to do this without this cluster expansion by looking at a completely different problem. I was asking myself, how can we get uniform bounds for matrix models of this type? And the cluster expansion was not working the ordinary way. So we found another method which we call the loop vertex expansion, which doesn't require Meyer expansion of cubes to compute connected quantities. So it was not by attacking directly the problem, but by looking at the side. So I think if we have...
I completely agree with diversity, and that...
Be patient.
Yeah, I think so. And I mean, you've done such wonderful work, and it would be good to see this come to fruition. And actually to get, in the end, improve some of the axioms.
So we should keep this in mind.
And John, did you have any comment?
Just on when you were
quoting Balaban's result on Yang-Mills in 4 dimensions. There's actually some of that missing. The perturbation theory part of that is missing. So there's actually no result for Yang-Mills in 4 dimensions.
The perturbation part is missing.
Yes.
You mean the beta function?
Yeah.
So he has not the usual normalization group dependence on the cutoff?
Well, he makes reference to another paper in which he says, in the early papers he says this is going to appear in a subsequent paper. In the last paper he says, well, it's all finished except for this one, which we're not going to do. And I took it to be just...
So did you try to do it with, in your methods with Hurd and Bridges?
Not Yang-Mills, no.
No, are you, but that's not on the table for you.
Not anytime soon, no.
But there has been work on this by Cooper and Müller. So they have written proof of perturbative. The problem is they don't use dimensional regressive. They use momentum cutoffs. But there has been, using the Polchinski equation, they have done rigorous normalization of Yang-Mills perturbative.
Yeah, but Balaban has a special
No, not Balaban.
setup.
Cooper and Müller.
Yeah, I understand, but I mean, they wouldn't necessarily help him because his is, idiosyncratic to his method. I mean, he left the impression that he knew exactly what to do, and he just wasn't doing it.
Yes.
Quick question.
Maybe those were the notes that were lost.
That's what I was thinking. Yeah.
Quick question. It's more of a philosophical question, but in three-dimensional Yang-Mills theory with adjoint scalar, for example, there's a solution by Polyakov by semi-classical methods. And instantons play a crucial role, right? And it maps to a Coulomb gas. And he shows that by semi-classical methods, there is in principle a mass gap. So there are two questions. Whether the same problem is addressed by constructive quantum field theory methods. The other one is, what is the meaning of an instanton in the constructive field theory methods?
Well, there are many cases where those methods do come into constructive field theory. So, I mean, there are duality transformations in the Sine-Gordon model that allow you to show that there's Debye screening and a mass gap. And related things, Tom Spencer is going to talk about duality questions in his talk. Which day is that, Tom?
Thursday.
Thursday. But
what's your opinion on the?
Well, I mean, I could have talked a little about duality. This particular, I have no opinion about the Polyakov paper that you mentioned because I'm not familiar enough with it to say anything. So, but I think that any method that can be used should be used. Yes.
Are there, in cases where a theory is constructed, is there ever a uniqueness theorem, or any hope of uniqueness theorem?
Oh, yes, thank you. That's a very interesting question. And there was an abstract uniqueness type theorem proposed by Debruchin based on statistical mechanics types thing of Debruchin, Lanford, and Ruel. And in fact, in two-dimensional models, they actually announced that they had some uniqueness for ground states in 5/4 model in infinite dimensions, uniqueness for small coupling, and non-uniqueness for large coupling.
Did you say
And
dimensions?
infinite volume, I meant. But unfortunately, they retracted this work, and that's never been followed up. The only uniqueness that has been established, as far as I know, comes out of the cluster expansions. So there are many different ways to pass to the infinite volume limit using the cluster expansions. And in the examples where the cluster expansions are valid, in the single phase region where you have a unique ground state, all the ways lead to the same limit. And in the, say, 5/4 where you have symmetry breaking and more than one ground state, you specify boundary conditions on a large region, and you can establish the existence of two phases, but it's not known for scalar 5/4 single component whether there's more than two phases, but the cluster expansions don't show any other example. Now, this has been carried out for more complicated potentials. A picture of the phase transitions, John Embry worked this out. His cluster expansions parallel the Piragoff-Sinai type expansions in statistical physics. But maybe that doesn't answer your question.
Well, just to clarify my question, what I meant by uniqueness, suppose somebody else uses a different cutoff, a completely different cutoff, starts over, studying 5/4 theory in 2 dimensions.
Yeah. So there are a wide variety of cutoffs, and you can write down, conditions. This set of cutoffs and this set of passing to the infinite volume limit all give the same answer. But
you can't hope to characterize it axiomatically. A quantum field obeying the 5/4 field version.
Well, that was DLR's approach. They tried to to state they had a variational problem, which they said would have a unique solution, but it turned out their approach to uniqueness didn't work, and that really hasn't been investigated. So you could hope to do it, but it hasn't been done.
Couldn't you, in the end, check the nonlinear field equations and whether the correlation function satisfies them or not?
Well, that doesn't deal with the state.
Oh,
doesn't the Borel summability say something about uniqueness?
Yes.
Right. So in 5/4 you can prove Borel summability in 2 dimensions for small coupling constant, but that's. Does that show that it doesn't deal with a large field region?
At best, it would show that a Borel summable 5/4 theory is unique.
Yeah.
Ideally, one would show a priori.
But so you can answer one of your questions about cutoffs. If you have one theory with a certain set of cutoffs, it converges to the Borel-Sum. Another theory for other cutoffs, it also converges to the Borel-Sum lemma.
I know. It would, of course, if you could show the both Borel summable, they would agree. But the strongest form of existence in uniqueness would characterize what you want by saying it was an operator valued solution for 5/4 versions, and show that, in some sense, that's what we think is actually true.
Well, that, again, it's the same family of questions that is this question too, I would say, that I asked about, so that one was, given a family of theories, that it was only the type of family that we expect physically, and here we're saying, I think what you would want to do is put some norm on all the observables,
Right.
and given 2 theories which are sufficiently close together, show that only one can satisfy the axioms, excuse me.
Right. So the cluster expansion gives partial results in that direction, but it doesn't nail things down.
Yesterday we had some conjectures which would answer that question, namely that perturbations of the theory are given by local features. And in this case, well, it's a bit different from what one usually has, because we have an infinity of fields of dimension 0. But still, it should be some moduli space. And you get that
My
essentially.
question didn't involve a moduli space. Suppose that on some other planet, some mathematical physicists use a completely different framework for constructing 5/4 in 2 dimensions. How do we know that they come up with an equivalent theory?
Well, if he comes up with a family of 5/4, depending on coupling constant, which for coupling constant going to 0 reduces to free field, then it involves moduli space. And
so, for example, for pure gauge theory in 4 dimensions,
the answer would be there's no deformation because there are no gauge invariant local operators of sufficient small dimension.
I'm trying to keep you from defining the kind of question I'm asking you.
Oh, I'm sorry.
You could ask that any 2 such theories be algebraically isomorphic. That would be a uniqueness result. Formulate them as an algebra of observables.
What is theory?
Yeah.
You should see if you give the detailed structure of the algebra of observables, then it will be unique. But what we want to know is whether there's a unique algebra, whether there's a unique thing that you should sensibly call an algebra of observables or 4-dimensional gauge theory. four-dimensional gauge theory is defined by much less. There are the Yang-Mills equations, and you're looking for an operator value solution of them formally, which are based on combination relations. The details of the algebra of observables is like having solved it. If you say uniqueness subject to the fact that you solved the theory, then that's what would be unique.
So it could be you can write down a solution in closed form by using some new sets of observables. And
I'm not trying to do that.
no, but
I'm trying to ask whether two different communities of mathematical physicists who approach construction in different ways. Whether there's any hope of proving a priori that their constructions would be equivalent.
If the nets of Riemann algebras are equivalent, this is not very helpful. But there is a device to check whether two theories are equal. And that's whether the isomorphisms between.
I'm not clear that that's the output of the theorem should be. The input should be given some simple, more elementary properties. And then the output of the theorem should say, therefore, the nets are equivalent. What it means to say that four-dimensional Yang-Mills is doing is that an operator valued solution must be Yang-Mills equations, and then the combination relations leads in the end to equivalent nets.
So we need conditions to
we don't hypothesize that for that sector. The conclusion, not the hypothesis, of the theorem should be.
No, I understand. But, so we need a device to decide this question when are two nets equivalent.
We don't necessarily have to formulate in terms of that. Yes, in that term, yes.
so if you take a scaling limit of a Ising model, do you actually get one of the field theories we believe is the limit? Or if you take Smirnov's construction of the scaling limit of percolation, does that define, I mean, that's a conformal field theory in many ways, but does it satisfy the axioms of quantum field theory? Is it something that we really know in some other way?
Well, I got interrupted. I mean, just to throw out this slightly different approach to the question, I would say it's useful for a variety of reasons to have metrics, or at least norms, on the space of theories, where the space of theories is really taking into account all observables, either all correlation functions or some other complete description of the theory. And then the absolute minimal result of this type would be to say that if the distance between, if you perturb the theory in this metric by some very tiny epsilon, that under some conditions, say no marginal operations, there's no other solution to the axioms within that tiny region. So that seems like to be a very minimal type of thing to be able to prove.
But, coming back to the discussion yesterday, there was the idea that, coming back to modular spaces, because these are nice classical objects, that one should have finite dimensional modular space of deformations if they are local thermal states. Now, in your case, the space of polynomials is infinite dimensional. So in order for that to be true, one should be able to prove that there are no local thermal states in phi 2. What's the situation about that?
Well, Christian sitting next to you has studied these local thermal states.
So they exist. Yes. So then some of the ideas of yesterday were obviously wrong, because there is no. Okay. The point is, one would like. One of the things came up yesterday is some relation between the Hilbert space and the space of fields, like it exists in conformal field theories, but at short distance. Now, in the phi 2 theories, there is an infinite dimensional space of dimension 0 fields. So obviously, a partition function cannot exist. And that means that, well, the ideas we had that such a partition function would be related to local thermal states must be wrong.
But the partition function needs something with trace class operators.
I
Well,
understand you.
I think there is
Of course,
an
confess.
No,
Yeah,
in conformal field theory, you know that the vector space of local fields is the same as the Hilbert space. And if you say you have a partition function, a trace of L0, then this converges. That means in particular that you have a finite dimensional vector space of fields lower than any given dimension, which is not true in B-fine.
Well, yeah, that's right. I mean, that's that. And comparing to the things I was saying yesterday, this is why we put I started putting the restriction that we're going to consider theories of the gap in the spectrum of operator dimensions in the discrete spectrum. And then, as people correctly pointed out, the first sign that if you don't do that, you have problems is logarithms, and you really do have to change, various aspects of the frameworks and reflections. Obviously, these operators don't function the same way. If you talk about theories that are flows out of conformal field theories with this gap in the spectrum, then you can see that the problem dimension is not present. Well,
maybe it's a good time to have coffee.
Choose this time to come back. Are people happy with this late schedule?